Hi, this is Dr. Clark, and in this episode we're going to be learning about the directional derivative and the gradient. Let's get started. So the main ideas from this section are what is the gradient, what are directional derivatives, and then we'll see the connection between the two. We'll learn a few more properties about the gradient, and then at the end we'll do some examples. So to begin with, we need a little bit of a background on what are vectors. So a vector in Rn is just n numbers written x1 through xn with the angle brackets, or you can write it vertically as a vector. Each one of these you can think of as the positions in the coordinates, and sometimes as a vector notation we'll just write it as x. So x with a vector notation means all n numbers like that. We can also think of that position as a function of time, so x of t. And really what that would be n functions, where the first function gives you the x coordinate, the second function gives you the y coordinate and the z coordinate, or x1, x2 up to xn. So the gradient is going to be a vector, and it's going to be made out of a multivariable function. So if a multivariable function has three inputs, then the gradient vector will have three components to it. And it's just a vector with the partial derivatives of f, fx, fy, fz. In two variables, if it's just f of xy, then the gradient is just fx and then fy as a vector. And we use this sort of nabla notation, this upside down triangle. And what you can think of as the gradient is at each point in the domain, there's a vector associated with that point. And so in two dimensions, so here's a multivariable function, for example. This would be the partial derivative fx. This would be the partial derivative fy. And then we just have some random point. And at each point, we just compute those partial derivatives. And so maybe at the point 1, 1, the x derivative would be 2 times 1 times 1, which is 2, and the y derivative would be 1 plus the cosine of 1, which is 1.54, and then you make that into a vector and you draw it at that point. And as you move the point around, you get, different gradient vectors. So that's all the gradient really is for each point in the domain, it's a vector, and the values of that vector are just the partial derivatives. And you can do it in three dimensions as well. So if we have f of x, y, z, some function, you can compute the x, y, and z partial derivatives, and you can make for each point in 3 space the vector comprised by the partial derivatives, and you can move that point around. You can move it up and down, move it around left and right, and however you move that point, you get different values of the gradient, and the gradient just points in different directions. So that's what the gradient vector is, basically. If you want to connect it back to the chain rule, if you think of your position vector as x of t, y of t, then you can get the chain rule d dt of f at x of t, y of t by taking the gradient and dotting it with the derivative of the position. So this kind of has that f prime of g of x, g prime of x look to it. And so that's kind of nice. You can write the chain rule using the gradient in a simplified short notation that kind of looks like the other chain rule. Okay, so that's what the gradient is. The next thing we want to talk about is what are partial derivatives. We've seen how to compute partial derivatives in the x and the y directions, but it's also potentially helpful to know what the rate of change is in other directions. So what if you aren't just moving in the x direction or aren't just moving in the y direction? Can you find the rate of change in those directions as well? And the answer is yes, you can. So here's an example. Here's a multivariable function. And here's a point on that multivariable function. And what I've done is I've intersected that graph, that surface, with a plane, and I can do the plane in different directions. So if I put the plane parallel to the y-axis, then I get a curve, and that curve has a slope. The slope of that curve is the y partial derivative. If I put the plane parallel to the x-axis, again, that curve has a slope. Whatever the slope is at that point, that's the x partial derivative. But you could say, well, what if we put the plane at a 45-degree angle? There will be a curve. The curve will have a tangent slope, and that slope is what we call the directional derivative in that direction. So every point has a little slope to it in every possible direction, and you can see those slopes change depending on what direction you're looking. So in this direction, the slope appears to be going down, so I'd expect the directional derivative to be negative. In this direction, maybe the slope is going, well, maybe for a different point here. For this point, slope's going up, so there's a positive partial derivative, or directional derivative. Maybe in this direction, the slope's almost zero. And so the directional derivative is just the slope of the tangent line to the curve in the direction you're looking. All right, that's all it is. How would you actually get that? Well, what you would do is you'd go back and you'd think, well, how did we define partial derivative? We defined it by just taking the old Calc 1 version of derivative with f of x plus h minus f of x over h, and you just put a little h into the x coordinate if you want the partial derivative with respect to x, put a little h into the y direction if you want a partial derivative with respect to y. So to do in a different direction, we need to add a little bit of the h to the x and a little bit of the h to the y, so we're moving both in x and y, and the way we normally do that is by, we only want to move sort of 1 unit length. And so how do you move, h units? Well, if we take the unit vector as cosine of theta sine of theta for a given direction theta, then h times cosine will give you a little movement in that x direction, and h times sine will give you a little movement in the y direction. And because cosine squared plus sine squared equals 1, the total length of movement will be 1 unit. And so we'll be moving exactly 1 unit, or exactly h units actually, because it'll be h times cosine and h times sine. So that's what the directional derivative is. It's a limit as you move a little bit over in a certain direction from where you were, and you figure out that slope. Now what you might be wondering is, do you want to actually evaluate a limit every time you compute a directional derivative? Usually these limits are hard to compute, and it's not fun to do it by hand. And what I have to say to you is, you won't have to, because the gradient comes to the rescue. So if you've got a differentiable function, you can compute its gradient. Remember, the gradient was just the vector of partial derivatives. We can dot product that with any unit vector in any direction. And when you do that, you get the directional derivative, so you get the slope of the function in that direction. And this actually works for functions of 3 variables or more variables, actually. If you have a unit vector in any direction and the gradient, you'll get the rate of change of that function in that direction, which is pretty slick. And I'll show you how that works. So here's a point in my domain, right here. Here's my point. And here's my unit direction vector. So I can put v in any direction I want. Okay? And I've computed, so here, over here is a function. It's xy plus x. So I've computed the x and the y partial derivatives, as you can see here. And so v is my direction vector. And if I take the direction vector v and dot it with these values, fx and fy, that's what this number is. Okay, so as you can see here, it's the dot product of the vector, so maybe you can read that. The fx, the x derivative, and fy, the y derivative, dotted with v, my unit vector. And to see if you understand this, let's go over here. You can see at this point, if I'm pointing in that direction, it looks like I'd be moving up the graph. So I would expect a positive slope. And when I look at the value of my directional derivative, I get 1.86. So that's positive. What if I turn this back around the other way? Well, now I'm looking this way, so I'd be going down, and I get a negative number. Probably there's a direction where I could get the directional derivative to be close to 0. If I point this way, it's almost like it's moving along the graph without changing its height. Let's keep this direction, but let's see if we move the point over here. Now we're kind of pointing down this slope, so now my directional derivative is negative, right? But if I move it over here, then I'm pointing up the slope, so now my directional derivative is positive. And there's probably some point over here where I can get almost like a directional derivative of 0, almost like we're at a little point in space where it's flat in every direction, which is kind of interesting at the point 0, -1 there. Okay, so all the directional derivative is the slope of the curve in that direction. And depending on what direction I point, I can get all different slopes, as you can see in this directional derivative value. And all I have to do to compute them is dot product the unit vector with the gradient. So it's pretty easy. Compute the partial derivatives, put them in a vector, dot product with the unit vector. A few important things to know about this gradient. So first, we need a differentiable function so we can make the gradient with the partial derivatives. And then the function, depending on what direction you look, the rate of increase or decrease could be different. And what's interesting is the gradient will give you the direction of maximum increase. So the gradient always points up the hill, if you will. Okay? The rate of increase is equal to the magnitude of the gradient, which is nice. So if you want to know the maximum directional derivative, you just compute the gradient, take its absolute value, and that gives it to you. Opposite to the gradient, so in the backwards direction of the gradient, you get the maximum decrease. And what's interesting is if you go orthogonal to the gradient, the directional derivative is 0. And that should make sense because if you're orthogonal to the gradient, this dot product will be 0. So that makes sense why the directional derivative is always 0 orthogonal to the gradient. And a little property of that would mean that anytime you're on a level curve, you'll be orthogonal to the gradient. So the gradient will be orthogonal to level curves because level curves are where the graph is not changing in height. So that's kind of an interesting feature as well. And that's what this theorem actually says is the directional derivative is 0 in any direction orthogonal to the gradient. So as a level curve. All right. So we'll finish up with a few examples, and hopefully that will help you see how to actually do some problems with directional derivatives and computing the gradient. All right, so for example 1, the question asks, what is the directional derivative for f of xy equals x squared plus e to the xy at the point 2, 0 in these three directions? So what we should remember is to find a directional derivative, we compute the gradient of the function, which in this case is the x partial derivative, 2x plus e to the xy times the derivative of xy with respect to x, that's just y, and then e to the xy times the derivative of xy with respect to y, which is x. Okay, so that's the gradient. In particular, the gradient function at the point 2, 0 is going to be 4 plus 0. And then e to the 0 is 1 times 2. Okay, so 4, 2 is the gradient. And the directional derivatives really are just the gradient dotted with the three directions here. So the directional derivative in the direction 1/2 root 3 over 2 of the function at the point 2, 0 should just be, well, the gradient 4, 2 dotted with the direction 1/2 root 3 over 2. And that happens to be 2 plus the square root of 3. Okay, so things to notice. This should be a unit vector. The length should be 1, which it is. You have to have the gradient at a particular point, and you get a number. This 2 plus root 3, that is a slope. It is a slope in this direction for this function at that point. All right? So graph the function, pick a point, look in a direction, find the slope. That's what that number is. Okay, then it says, how about the direction 0, 1? Well, 0, 1 is the y direction. So this should actually be 2, which is the y partial derivative. So if you do the directional derivative in the y direction, you're going to get the y partial derivative. That's what the directional derivative is in that direction. And similarly, if we go in 1, 0, 1, 0, the x direction, well, we just get 4, which is the x partial derivative. So partial derivatives are actually included inside of directional derivatives, but you can go in any direction you want. And when these numbers are positive, that means the graph is on its way up in those directions. If these numbers are negative, it would mean the graph is going down in those directions. All right, here's another example. And this question says, show that the level curves to the function z equals x squared plus 4y squared are orthogonal to the gradient. So that was one of those properties we talked about. So if you have some function here, this is going to be kind of a bowl-shaped function, okay? And it'll be an elliptical bowl if you slice it. And the question is, if you looked at, for example, some particular level curve, and then you sort of drew that down in the xy plane, you would get, right, you would get like an elliptical level curve like this. And there should be a tangent line to that curve, and at that point there should also be a gradient, right? And it should be true that the gradient is orthogonal to the level curve. That's what we're trying to see here. So let's try that. First, what's the gradient? Grad f is 2x, 8y. Okay, that was easy enough. There's the gradient. What's a level curve? We'll pick some z0 value, right? There's z0. That's some constant equals x squared plus 4y squared. Okay? Now, so that's really just a curve down here in the plane, right? If you just sort of graph that, it's some ellipse. But hopefully you recall from a previous section that if you want a tangent slope, and you can write a function implicitly as some f of xy equals 0. So for example, capital F of xy is equal to x squared plus 4y squared minus your z0 value. Set that equal to 0. That implicitly defines that ellipse. Then the slope of the tangent line is equal to negative fx over fy, which would be, fx for capital F, that would be negative 2x then, over fy would be 8y. Okay, so that's the slope. So I need to turn a slope into a vector. Well, if the slope is rise over run, I could make this 1, and that would be 2x, negative 2x over 8y. That would be the slope. So this vector then would be the vector 1, negative 2x over 8y. That would be the tangent vector. And what the question says is prove that that tangent vector to the level curve is orthogonal to the gradient. So let's try that. What's 1, negative 2x over 8y dotted with 2x comma 8y? And I get, what do I get? 2x and then minus 2x equals 0. Okay, so two vectors, we dot product them, we got 0. When the dot product of two vectors is 0, those vectors are orthogonal. So there we go. And we did it not just, we did it actually for any level curve and for any random point xy on that level curve. So there you go. So that was just this example, but this is true all the time. All right. One last example here. So everything we've done works perfectly well for functions of 3 variables. So let's just do one more example in 3 variables. So L of x, y, z is some function that maps the light, so the luminosity at a particular point in a forest. So you've got some forest here, and no matter where you are in that forest, maybe you're right there, there's a certain amount of light that gets to that point, and you could quantify how much light that is using some light measurement device. Maybe if you're under the tree, it's darker, there's less light there, there's probably more light there. Okay, so let's pretend that the amount of light available is given by this function right here, 10e to the z over 1 plus e to the z times 2 plus the sine of xy. The sapling is located at the point 1, 0, 0. And in what direction should the sapling grow in order to most quickly increase its light availability? Okay, so let's say the sapling starts growing right here and it wants more light. Well, it should grow in the direction of more light. And we already saw a little bit ago that the gradient is the maximum direction of increase of the function. So it should grow towards the direction of the gradient. Okay? Now, before we do this, probably you might wonder, well, how is the plant going to know how to compute the gradient and then grow in that direction? Well, it's probably not going to compute the gradient, except if you do imagine you have a leaf here, and a certain amount of sun hits here, 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 and here. It could probably figure out there's more sun hitting here than there, more sun here than there, maybe. And so it can sort of figure out that this is the direction it should go because there's more sun in that direction. And so it's sort of not computing, it's not computing the directional derivative using calculus, but it is actually doing sort of a, it can tell a difference in luminosity from one part of the leaf to another, and that can actually sort of tell it which direction to go, which is actually using the idea of the gradient. Okay, but let's do the calculus for the plant in this case. What is the gradient of this function? Well, I need the derivative with respect to x first. Okay, well this 10e to the z over 1 plus e to the z, that's basically just constant. And then take the derivative of the inside. Well, that's 0 plus cosine of xy. And then differentiate with respect to x. You get a y that comes out. Then it'll be similar when we compute derivative with respect to y. We'll get cosine of xy times x. And then we'll need the derivative with respect to z. I'll write this down here probably. So we've got a little bit of a quotient rule. So let's see, we need low d high minus high d low over the square of what's below. And then 2 plus the sine of xy is constant. All right, so take the gradient at the point 1, 0, 0. So I guess what, x is 1 and everything else is 0. So we get 10, because e to the 0 is 1, 10 over 2 times 0. Okay, so there's going to be a y there, that'll be 0. And then we'll get 10 over 2 times cosine of 0, which is 1, times 1. So that'll be 1. And then we're going to get, okay, sine of xy will be 0, so there'll be a 2 here, times whatever this quotient is. E to the 0 is 1, so we get 2 times 10, I guess, is 20, minus 10 times a couple of 1s. 20 minus 10 over 2 squared is 4. Okay, so what's the gradient in this case? 5, 0, 10 times 20 over 4, 505. Okay, 505. So that would be the gradient, and we want to move in the gradient direction. So we probably should go in the, to make that a direction vector, we need to take the vector 5, 0, 5, divide by the length of the vector 5, 0, 5. And the length of 5, 0, 5 is 25, plus 25 is 50. Square root of 50 is 5 root 2. So 5 over 5 root 2 is 1 over root 2. 0, 1 over root 2. Okay, yeah, so this is 5 square root of 2 is that length. So if we just divide the vector by the length. Now we've got a unit vector. And anytime the problem asks for a direction, direction means unit vector. So keep that in mind. Direction means unit vector if you're working a problem. All right, so there's some examples and some explanation of gradient, directional derivatives. Hopefully that helps you to understand these ideas a little bit better.